Hey guys, sorry I've been needing to finish these up, so I thought I would do the last day of rational functions and then go from there. I think I'd like to maybe introduce at least polar to you in this next week, so I'll send you some messages and go from there, okay? So for the last day of graphing rational functions, or exploring them anyway, as well as graphing. First, just given a rational function, um, determine the end behavior. So end behavior is the behavior as x goes to the infinities. So we're talking about as x goes to negative infinity, what is y approaching? And as x goes to positive infinity, what's y approaching? So there's actually two different things I could be asking you to find. I could be asking you to find the exact end behavior model, or I could be asking you to find just the end behavior. So just the end behavior is actually pretty easy to find. If you're just looking for the end behavior, what you can do is think about the powers. Because the higher power is in the numerator, you can take the most powerful terms and divide them. X cubed divided by x squared simplifies down to x. So we're basically looking at the same end behavior as a linear function with a slope of 1. Now, if I actually want to find the end behavior model, then I can find, is that slant asymptote um, here, or is it like, say, here, or is it right here? And that would be necessary in order to be able to sketch the graph, actually. So I do know that the end behavior of x, which is an odd powered positive leading coefficient linear function. So as x goes to positive infinity, the function is going up to positive infinity. And as x goes to negative infinity, the function is going down to negative infinity. Okay, but if I actually wanted the end behavior model, I would have to do this the long division. So I would have to say x squared plus 5x plus 6 divided into x cubed minus x squared plus 5x minus 4. So I need to multiply x squared by x to get x cubed. So x times x squared, x times 5x, x times 6, and then subtract. So minus, minus, minus. And then this becomes negative 6x squared. Technically I'm done after, like, I don't need these other terms because I only need up to the constant, or down to the constant, I guess you could say. So I need a negative 6 in order to multiply, in order to get negative 6x squared when I multiply by x squared. So negative 6. And then, like I said, everything else is just remainder. So as soon as you get this, then you actually get the end behavior model. So the end behavior model would be y equals x minus 6. That is the actual slant or oblique asymptote that this function has. And so it is actually down here 1, 2, 3, 4, 5, 6. Slope of 1, y-intercept of negative 6. That would be the oblique asymptote that we would need to graph. Okay? All right, but as far as in behavior, I already had it just right there. Find the end behavior for the given function. Okay, so look at the powers. The higher powers in the numerator, so I'm just going to take this and simplify. 4x cubed divided by 2x is 2x squared, which is a positive quadratic. So that I know that in the end, the function in both cases going to positive and negative infinity, as x approaches both positive and negative infinity, the function is going up to positive infinity. Now if I wanted the actual end behavior model, I would have to, like I said, do the long division. So that'd be 4x cubed plus 0x squared minus 16x plus 0. I don't even know if it's, I'm just going to see what it would be what it would look like. So 2x squared. So 2x, yeah, 2x squared times 2x is 4x cubed. And then that is minus 2x squared. Subtract, so minus plus. And that becomes 2x squared minus 16x. Bring that down. I would need to multiply by an x. X times 2x is 2x squared, and then minus x. And then subtract. That becomes negative 15x plus 0, and then the last number I need is the constant, so then I would have to multiply 2x times negative 7 halves, no, just kidding, 15 halves, in order to get 15. 15 times 2 divided by 2 is 15. So that would be negative 15x, blah, blah, minus, or plus 15 halves. Doesn't really matter. That would be the actual oblique, not oblique, parabolic asymptote, if you will. So wherever that function is, I have no idea. I know it crosses at negative 7.5, but I don't know where the center is. Um, I just know that it would be something, I'm just pretending, that's probably not even the minimum. Whatever. It could go like this. So whatever the function looks like, in the end, it would follow this. Okay? But as far as in behavior, we were done. Okay, so now what I want us to do is I want us to consider how we're going to draw or write a function that meets all this criteria. Yeah? So I challenge you to pause it, write these down, and then try and write a function that meets these criteria, okay? All right. So for the vertical asymptote, I know that in order for there to be a vertical asymptote at 4, there needs to be a factor x minus 4 in the denominator and not in the numerator, or at least more of them in the denominator than the numerator. X-intercept at negative 3, 0, I need there to be a factor x plus 3 in the numerator and not the denominator. For a whole at x equals 1, I need there to be a common factor x minus 1 in both the numerator and denominator. Or at least, yeah, the same number of times that need it to be in both. Although I could have more of them in the numerator, it would just mean, well, we'll talk about that in a second. So I took care of that. And then I need a horizontal asymptote at y equals negative 1/2. Now I'm going to expand this, not because I need to, but just to be able to talk about it a little bit more easily. If you expand the numerator, you get x squared plus 2x minus 3, and in the denominator you get x squared minus 5x plus 4, right? If I asked you, what's the end behavior, or the horizontal asymptote, I would hope that you would think, okay, let me look at the powers, right? So the highest power in the numerator and the highest power in the denominator are the same, which means if you go back to our rules, it's the ratio of the leading coefficients 1 divided by 1. That would be 1, but I need it to be negative 1/2. So I could either just make this one a negative and distribute the negatives to the top, and the denominator make it a 2 and distribute that to the denominator, or I can make the denominator a negative 2 and distribute that. Multiplying by this by a constant negative 1/2 does not change any of this. Okay? So now I've met that criteria. So my final answer would be negative x plus 3 times x minus 1 over 2 times x minus 4 times x minus 1. And for the problems that I am going to assign as far as practice goes, I'm okay with you leaving it in factored form. You don't have to multiply it out and expand it. Okay? All right. Okay. Now, having done that one, I'd like you to pause it again, write this down, and then try it yourself. I'm going to go ahead and... Actually, just kidding. The first thing I want us to do is I want us to pretend like that was a 3. Some of y'all probably already paused it. I'll go back to it being 0. Okay. So, okay, vertical asymptote x equals 2. Cool? That means it's in the denominator. X minus 2, a factor in the denominator. Now, I will say this. If I had this, but then I had that would still work. As long as there's more in the denominator than the numerator, it's still going to be a vertical asymptote. The whole won't matter because the vertical asymptote will overtake it. Okay? But either way, I've taken care of that. X-intercept. X-intercept means factor in the numerator, so that would mean x plus 5. I didn't really branch off of sides, or signs, did I? Okay. A whole at x equals 0. Okay, so you could think of it as a factor x minus 0, but it's easier to just think x, right? So if I would just put an x here and an x there, then there we go. Okay. Now I need a horizontal asymptote at 0. Okay. I need a horizontal asymptote at 0. A horizontal asymptote at 0 is a situation where, because remember you got 3 different options for your rational functions as far as horizontal asymptotes. You can have the higher power in the numerator, which means no HA, you've got polynomial asymptote. Polynomial asymptote. You can have the higher power in the denominator. That automatically means horizontal asymptote y equals 0 because the denominator is growing bigger, faster than the numerator, which means the number is getting smaller. because you're dividing a large number, could be even increasing, or it could be just a constant divided by an increasingly large or larger number. Or they can be the same power, in which case you have a horizontal asymptote at y equals the leading coefficients. Okay? We are in a situation where these are the same power. This is x squared plus 5x, this is x squared minus 2x. This would not give me a horizontal asymptote at y equals 0. I need the higher power to be in the denominator, not the same. That would be a horizontal asymptote at 1 in this case. So, I need to increase the power of the denominator. Now, I can do this two different ways. One way that I cannot do it is by increasing the power of x. If I were to increase the power of x, then that would make this a vertical asymptote at 0 because there's more x's in the denominator and the whole would no longer matter. So I need that to still be a hole in the graph. I could change this, and that is a valid option. It does change something about the graph though. So I do have a vertical asymptote at -2, but um, sorry, give me 1 second. Alright, so when you have a vertical asymptote, um, if you have an odd multiplicity on that, that means that you're going in opposite directions. Like if one goes to negative infinity, the other side goes to positive infinity. But if I change that to a power of 2, that means they both go in the same direction. So if this goes to negative infinity, this goes to negative infinity. I call it the bounce of vertical asymptotes, if you will. Okay, so that's another option. There's another, or that's the first real option I've given you. The other option, which kind of is, it's not necessarily sneaky. It doesn't. It's kind of like what do the directions say? Can it only meet this criteria? In which case, then we definitely need to do this one. But if it can meet more criteria, then I could just make up some other crap and say, well, there you go. Now I have a power of 3 in the denominator, a power of 2 in the numerator, and I have another vertical asymptote. Cool. So if it said it can only have a vertical asymptote at x equals 2, then I would have to do this step. But if it was, it does have these characteristics, then you could do that. And so honestly, on the homework, I'm going to accept either type of situation. And by homework, I mean practice. Okay. Um, I think I'm going to go ahead and call this first video, the first part done, and then I'm going to pick up with the next part, okay? Just so they don't get too long.